Hey folks, welcome back. Today we start on topic 5, which is Gauss's law. Topic 5 is covered in the second exam. So our second exam covers topics 3, 4, and 5. It's capacitance, electric forces and fields, and Gauss's law. Okay, so what is Gauss's law? Before we show you the slides, what is Gauss's law? Gauss's law is a mathematical tool that we use to calculate electric fields. I know we already have some tools to calculate electric fields. It's just one more. And Gauss's law is a little bit complex on the front end because it's very mathematical. But what we find is that once you get comfortable with it, it's generally a quite simple way, easier way to find electric fields for certain distributions. So remember that as physicists and engineers, what we want is we want a whole toolbox, right? An entire toolbox of physics tools. And when we encounter a problem, we want to be able to have a choice in how we find or what tools we use. So Gauss's law will help us find E fields. Okay, but before we get there, I've got to get through some definitions. So what is Gauss's law? Gauss's law, what is it? It's a tool. It's a mathematical tool. It's heavily mathematical that is used to calculate the E field on a material with many charges. So we've already seen that Coulomb's law works great for a few charges. That's one way to find the electric field. We have another way to find the electric field, way number 2, when we had lots of charges where we could do k sub e and then that integral dq over r squared. That's way number 2. But Gauss's law is going to be way number 3. All 3 paths and avenues should get us to the same answer because they're all doing the same thing, helping us find the electric field. And which one you use is entirely up to you. But Gauss's law is kind of a giant in the world of electricity and magnetism, and we'll see why. But we've got to get through some definitions first. Why? Because Gauss's law is totally and completely related to the electric flux, which means that, well, we got to know what electric flux is. So electric flux is basically the measure of how many electric field lines pass through a given surface. So you can imagine that the more electric field lines, the denser it is, the more electric flux. The less or the fewer electric field lines, the smaller the electric flux. So we're going to need to understand electric flux because Gauss's law is totally related to the electric flux. So first, let's go there. Let's talk about flux. So the electric flux is denoted by phi, and then because it's electric, we're putting the subscript E in there, because later on, when we look at magnetism, we'll also talk about flux, but it'll be now the magnetic flux. So we just want to be able to differentiate. So the electric flux is proportional to the number of field lines that pass through the area, but wait, one more piece. The number of perpendicular field lines that pass through that area, right? So here's an area, and all these lines are already perpendicular. They're already normal to the surface. But in the bottom drawing, there's an angular component between the normal to the surface and the electric field lines. Well, the electric flux is going to measure the electric field lines that are normal to the surface. So there's a couple ways to write this. So also, why do we want it? Well, imagine that the electric field lines run parallel to the surface. Well, then there's no electric field lines passing the surface. They're not going from like the left side to the right side. They're going through the surface. Imagine that the surface is a wall, and I want to know, or like a door, and I want to know who passes through the door? Well, I need you to go from one side of the door to the other side of the door. If you're running like through the door, it just doesn't work. So that's why we look for the normal component. We want them to go from one side to the other. Later on, what we'll see with Gauss's law is Gauss's law requires a closed surface, which means there's going to be an inside of the surface and an outside of the surface. So we need to be able to see the electric field lines that go from outside to inside or from inside to outside, not along the wall. That's the whole like normal component to it. You want the lines that are normal. So therefore, we can write this in a couple ways. It is the electric field lines passing through that area, but we need to make sure that we're just looking at the normal component. And you say, wait a second, but why is that theta? Isn't the normal generally sine? Well, it all depends on how you define theta. Theta is not being defined from the surface to the E fields. Theta is being defined from the normal to the E field. Okay, so the normal and the surface always make 90 degrees to each other. That's the definition of normal. Right, so here's the normal and here's the surface. They're going to be at 90 degrees. That's our definition of normal. And our theta is going to be measured from the normal. Electric field has units of newtons per coulomb, and area has units of meters squared. So super important to remember that theta here, this cos theta, is between what? Between the normal to the plane of the area and the E field. Between the normal to the plane, not the surface, but the normal, and the E field. There are many ways to write this. Many ways to write this. Sometimes we write this as such, where we say, wait, the electric flux is the normal field lines to the area. And again, we just then expand that normal field lines. Well, it's E cos theta. It's the component of the E field normal to the surface. So just know that it's sometimes written differently, right? Sometimes it's written as, sometimes it's written as the flux is the perpendicular to the area, the normal to the area. They're all saying the same things. Figure out where the normal to the surface is. Figure out the orientation of the E field lines. Get the angle between them. Take the cosine, multiply it all together, and you got yourself your flux. So, with Gauss's law, what we're going to see is it's really important to have a closed surface, an inside and an outside. That's what a closed surface is. So imagine that this is like a balloon of some sort. There's clearly a place that's inside the balloon, that has like the helium in it. And then there's clearly a place that's outside the balloon, like our regular atmospheric air with like oxygen and nitrogen and stuff. So what we're looking for is the electric field lines that are going to go from inside to outside or from outside to inside. So we're taking some steps here to figure out how we find the flux, because the flux is going to connect us to Gauss's law. Okay, so we're looking at this electric field line, whatever it is, and whatever orientation it is, and then we need to find the normal to the surface. But if I have a curved surface, it's no longer a flat sheet, right? In the previous slide, I had a flat sheet. The normal didn't change throughout that surface. Here, the normal changes. For this little element, this dA, well, the normal is that way. But I could assume that if I choose a dA this way, the normal is going to point in a different direction. And over here, the normal is going to point in a different direction. right? And in fact, if I have like a sphere, like the normal, say, like at the North Pole, hello, is going to point up. The normal at the South Pole is going to point down. The normal at the equator is going to point right or left. So as I move around the surface, well, the normal is changing too. So with Gauss's law, we want to be able to incorporate weight, but if the normal is changing as I move through the surface, how does the mathematics look? So we're going to get there. We're going to get there. So for each little bit of area, right? So the first step is to break this down into little bits. And maybe we see that eventually what we're going to do is integrate to bring all those bits together, because that's what integration does. So we start with little bits, and now let's define this. Delta A vector. You go, wait, A vector? Since when is area a vector? Oh, since physics. Because I need to know not just like what is the area, like what is the meters, like the square footage, say, but also like, is my normal pointing this way? Is my normal pointing that way? Is my normal pointing this way, that way, that way? Where's my normal? It changes with every little element. And that's why we give it the little vector notation. Because now I need to know how the E field lines up with that normal. I need that angle theta. It's super important to have that angle theta. So let's define those little elements of area, okay, as having magnitude of, well, area, and having a direction that is, hey, normal, perpendicular to that surface element. Okay, so for each electric field line, you need to know what the normal looks like at that location. So then we take all of those little elements all over our blob, every single one of them, right? And we add them all up, but you know, you can do that till the cows come home, so let's just make it an integral. I really don't know why they even teach all this limit stuff. Like, let's just jump straight into integrals, can we? Okay, so the electric flux then is every little electric field with every little bit of area turned into an integral. But hold on, what's that little dot there? Oh, we're getting into vector calculus. Vector calculus. Wait, that's a dot product. Dot product looks for what? Looks for parallel components. So that's where the cos theta comes in, right? A dot product, remember that, well, let me see. Let's do random vector A dotted into random vector B is magnitude A, magnitude B times the cosine theta. In other words, it looks for parallel components, just like that. I want to know how much of that E field is normal to that. So it's the projection of one vector onto another with its parallel components. So first of all, every little element of area with every electric field line, its parallel components. Well, I can write that then as E dot dA, and then add them all up or turn it into an integral. And it says surface integral because I'm going to, have to integrate every little bit all over this surface. So this is our first piece of the puzzle that's going to go into Gauss's law. But that's not Gauss's law yet. This just tells us the electric flux. Now, it could be that our electric field is constant, and it could be that it's changing. And if it's changing, it's got to stay inside the integral. Then if it's constant, it can come out. But remember, it's called vector calculus, not calculus vector. What that means is do the vector first. vector calculus. First the vector, then the calculus. Okay, so the first thing I have to do is take care of that dot product, get that parallel or whatever, and then attack the calculus. Not calculus vector, vector calculus. Okay, so what does that look like? Well, like a whole hot mess, kind of, until Gauss comes and like really solidifies this for us. So imagine we've got a surface here like this blimp, and I can imagine that every little surface element is going to look different, right? Like over here, it's going to look like that, and my dA points that way. Well, over here, it's going to look like this, and my dA points that way. On the bottom, my dA points that way. But the electric field lines are just running in that direction. So that means that for every one of these, there's going to be a different angle, right? And you can see here, it's the projection. How does the electric field project onto that normal? Well, that's that dot product. That's exactly what the dot product is. It's the angle between the normal to the surface and the electric field. That's the dot product. Now there's all this stuff about is it positive or negative? You know what? Let the math do it for you, because cosine sometimes is positive and cosine sometimes is negative. So let the math figure out those signs for you. Yay, math. Right? So all this stuff about negative and positive, well, yeah, if they're like leaving, if there's more lines leaving than entering, what does that mean? Is that positive? Is that negative? Or you just do your cos theta, and for any theta greater than 90, you're going to get a negative number. For any theta less than 90, you're going to get a positive number. And for theta equals 90, you're going to get 0. 0, right here, 0. This electric field line is neither, like, it's not going from the inside of the surface to the outside of the surface, right? The inside was over here. Come on, right. Inside was over here. Inside the blimp was over here. And outside the blimp was over here. Well, that line isn't going inside and outside. It's going along the surface of the blimp. It doesn't contribute to the flux. But I can totally let the math do it for me. I go, hey, there's the normal. Hey, there's the E field. Hey, 90 degrees, cos 90 is 0. Badam. Done. Okay, so let's write this mathematically a little bit more. Symbol here, integral with the little circle, that just means it's a closed surface because Gauss's law only works with closed surfaces. I've got to enclose the surface that I'm talking about so that there's a clear inside and a clear outside. Once I have that, then I can write the electric flux, right? I can say, right, it is vector calculus. It is the dot product, the parallel component of the E vector and the dA vector, but I have to remember that dA is normal to the surface, not along the surface, which I can also write as En times dA. Now there's no dot product. There's no dot product anymore. It's gone away. And my vector notation has gone away because I'm already calling that as the part of the electric field that is normal to the surface. We'll see this in action. I'm a firm believer that we learn by doing, right? But notice how these all say the same thing. All right, so let's look, for example, at this, what is this shape? It's a cube. That's what it is. Let's look at this cube. And we want to know, what do we want to know? We have an electric field that points in this positive x direction, and we want to find the net electric flux. Cool. So that's what's eventually going to lead us to Gauss's law. So it's great to take this step. So what do we have to do? We have to look at all the surfaces. So in my let's do these in pieces. Let's do this surface 3. Well, the surface is flat and parallel in the xz plane. So the normal points in the y plane, right? There's my normal. And which way does the electric field point? In the x plane. How much of that electric field is coming from the inside of the cube to the outside of the cube? None of it. It is running along the surface, along the roof, if you will. And not coming into the room, it's just passing along the roof. So it doesn't contribute. But I can let the math do it for me. And I can see the same thing is going to happen on like the floor side of the cube. Those electric field lines aren't coming into the room. In order to come in and out of the room through the floor or the ceiling, the electric field lines would have to be up and down. Right? But they're not. They're left, right. So they're not going from the inside to the outside. But that's okay. I can let the math take care of that for me. What about this side 2? Well, side 2 is in the YZ plane, and the electric field lines point in the X plane. The dA, the normal vector, points in the X plane. Hey, the electric field lines are going from inside the cube to outside the cube. They're going to contribute to the flux. And I can see the same thing is going to happen with face 1. What about the front and the back faces? They're not labeled here, but we could label them 5 and 6. They're in the XY plane. And the electric field is in the X plane. Again, they're just running along the wall. They're not coming in and out. Well, that's fine, but I keep telling you, let the math take care of it for you. Well, let's do that. Let's let the math take care of it for us. All right. So let's call these 1, 2, 3, and 4, just like following the picture. Okay, so I'm not going to redraw a cube because trust me, you don't want to see me try and draw a cube. I'll have a meltdown. You have the picture for reference. So let's look at face 1. Okay, so face 1 had our dA element kind of pointing that way, and the E field pointing to the right. So the theta is 180 degrees, and cos theta then becomes -1. What about face 2? Face 2 had our dA element pointing that way. E field isn't going to change, it points that way. So theta is equal to 0, not 90. Theta is equal to 0 degrees. And cos of 0 equals +1. What about face 3? This is like the ceiling, right? dA points upward. E field still points in the positive x. That hasn't changed. What is theta between them? 90 degrees. What's the cos of 90? Cos of 90, 0. Okay, what about face 4, like the floor? Well, dA points down that way. Electric field still points that way, to the right. What is the theta? Hey, 90 degrees again. Still 90 degrees. Still, cos of 90 hasn't changed since last time. It's still 0. And for faces 5 and 6, it's hard for me to draw. 5 would be like facing us, like out of the page, dA, right? So like out of the page, like a vector coming out towards you. And E is to the right, 90 degrees, 0. And for 6, it would be like into the page. For 6, it would be into the page. Hold on. Let me redo this. Okay. For 6, dA is like into the page, which we can draw like this, like the backside of a vector. And E is like that to the right, so still 90 degrees and still a flux of 0. So the only ones contributing are face 1 and face 2. Cool. All right, so what is the total flux? Well, it's going to be the flux for area 1, E dot dA, plus the flux for area 2, E dot dA, plus the flux for area 3. That did not make sense. The flux for area 3, E dot dA, plus the fourth face, E dot dA, plus the flux 5, E dot dA, plus the sixth one, E dot dA. And keep in mind that every single one of those E dot dAs is magnitude E, magnitude A, times the cos of theta. Now we already found the cos of theta for all 6 of those. Okay? So if you go back and look at the other whiteboard, this one became E A basically times 1. The first one was -1. This is going to be integral EA. Face 2 was just +1. 3 was 0, 4 was 0, 5 was 0, and 6 was 0. So the total flux, is just integral negative EA plus EA equals a big fat 0 equals 0. Wait, we did all that work for this to equal 0? Kinda. Yeah. So let's think about this. It's a closed surface, and just as many, the electric field lines are coming all the way from the left side of this cube, all the way from the left side of this cube to the right side of this cube, following that x direction. How many are coming in? 2. How many are going out? 2. How many stay inside? What is the net? 0. So I like to think of flux as students entering a room. There's a back door, there's a front door. How many students are in the room? Well, if just as many enter than leave, there are no students in the room, which is what's happening here. If I want there to be students in the room, then I don't want a net flux of 0. I want some students to stay. And what would that look like? Well, the electric field lines would have to originate from the inside and go out, or go like in, radially inward, something like this. then I would have, like in this case drawn here, I would have a net influx of students. If there was electric field lines that left like this, there would be a net outflux of students. But in this case, there's a net zero. They all come in through this door, they all leave through that door, no one stays. It's kind of a silly example, but we're going to build on this. And we're going to see, this isn't Gauss's law yet, but we're going to see that we can do this with Gauss's law just by looking at it. All right. Gauss's law. Because that's what we're trying to get at, right? Well, Gauss's law is a mathematical tool, but it's also going to help find electric field, and it's going to do so first. There's a couple steps. We're not getting to the final form yet. First, there's going to be a relationship between the net electric flux through a closed surface, so we're going to call that our Gaussian surface, and the charge enclosed by that surface. Okay, so let's go back and remember, like if we just have a positive point charge, right? And we want to know what is the electric field at point P. Well, we know how to do this. We know how to do this. We can use, one of the tools we can use is to say, okay, at point P, so what would happen if I put a positive charge there? Well, it's going to go radially outward. So I know the electric field points in that direction. And if I know the R, I can find this by just doing KEQ over R squared, right? Well, we're going to see how to get this same exact answer, but using all this flux stuff. So if we want to know what the electric field is at point P, the very first thing we're doing is we're going to create our Gaussian surface, because Gauss's law requires there to be a closed surface. So if my charge is like a proton or like a spherical distribution, I'm going to take this point P, and I'm going to like create a surface, a full surface, like a full balloon. It's not a flat disc, it's a balloon. And I'm going to place the charge inside this balloon. Is this balloon real? No. It is a Gaussian surface. It's a Gaussian surface that is a mathematical tool. This Gaussian surface is not real. Gaussian surface is not real. If I want to know what the electric field is at point P, then at point P, I create a balloon, a whole sphere with that charge inside. And then I look at the flux. I say, okay, for this little element of area, well, it points in that direction. The electric field points in that direction. What's the angle theta? Theta is 0 between them. What's the cosine of 0? It equals 1. Cosine of 0 equals 1. Okay, so what is this Gaussian surface? It is a mathematical tool, not real. I'm going to place it at point P. Where do I want to know the electric field? And I have to make sure that it's a closed surface, a balloon. Okay. Then let's apply Gauss's law to this. So, okay. So I have a little positive charge here, and I want to know what is the electric field at point P. I could use my Coulomb's law, yes, but let's practice using Gauss's law, because later on we'll see charges that look different. Okay, for example, wait, let's hold on, let's do an aside. What if I have a positive distribution that looks like that. And I ask, what is the charge P? Well, I can no longer do Coulomb's law. And, my R is changing drastically from every point. So I can maybe dq over R squared and figure all of that out, but that's getting kind of difficult to work with. So instead, what I can do, I want to know what it is at point P. So here's point P. So instead what I can do is I can take a Gaussian surface and place it there and enclose the whole thing like a balloon and do that. Okay? All right. So back to the problem at hand. We have that charge distribution just like a little proton. Not necessarily a proton. Now I want to know what is the charge at P. So this is a balloon, not a disk. A balloon. It's coming out towards you. There's a front, there's a back. It's a whole sphere. And then I say, well, it's a positive charge. So any electric field placed there, will be repelled. And the electric field points out this way. And for this little element, the dA also points that way. And likewise, if I come over here to this point, what does the electric field look like? Electric field would point out this way, and the little element of dA would point this way. And I could really ask about at any radial distance r, what is the electric field there? Okay, so for any and all of these, theta is equal to 0 and cos of 0 is equal to 1. So the electric flux is the closed integral, okay, of E dot dA. So do the vector part first. So this is E A cos theta. And cos theta is just 1. So this equals EA. That's the flux. Okay. All right. Well, now at this point, we're not quite ready to use Gauss's law in its full form yet because we need to equate it to something else. But let me go back and see what we're yeah. Okay. So we kind of know what E looks like, right? At that point R, we know it's just KEQ over R squared. So we can replace that and we would get KEQ over R squared. And what is the area of that sphere, surface area? 4 pi R squared. And you basically get things to cancel and come out of the integral. KE is a constant, Q is a constant, 4 is a constant, pi is a constant. And you get that the electric flux is just, where'd it go? 4 pi KEQ. So I kind of skipped a step though. That's why I was hesitating. Let me redo this. I skipped a step and I tell you all not to skip steps, but then I did it. So let me redo that. So because I know what the answer was, I skipped some steps. So come all the way back to here. This is magnitude of first vector, E. Magnitude of second vector, it's still dA, cos theta. Okay, so let me write that on a new whiteboard. I want to make sure I take all the steps. So far we've got that the flux is integral magnitude E, magnitude dA cos theta. Okay, now cos theta, remember, was just going to give us 1 because theta was 0. So my electric flux is, first do the vector, done, E dA times 1. That's the vector part. Now do the calculus part. Does the E field change along that Gaussian sphere? No, it's the same. That's what we were saying, like whether I look at whether, if this is my charge over here, it doesn't really matter where I choose to evaluate the E field anywhere on that sphere. Anywhere on that sphere, it's at the same R because it's a sphere. It's going to have the same magnitude. What's going to change is the direction, right? But hey, this is now just a magnitude. I don't see a vector symbol. So that's a constant electric field. They're all the same at every point along that Gaussian surface. And then I just have integral dA. And once I have that, now what happens when I integrate every little element of area? Whoops, I keep forgetting these. Every little element of area over the whole area, well, I just get the area back. So this is just E times A. That's it. E times A. And what is A? Well, A, it's the surface area of that balloon, a spherical balloon, 4 pi r squared. Okay? So the flux is the electric field times 4 pi r squared, and we know what the electric field is. It's KEQ over r squared times 4 pi r squared. So the electric flux at that point is a positive KEQ times a 4 pi. All of this is just to help us get to Gauss's law. So we just want to get to Gauss's law. Gauss's law will eventually help us find the electric field. Here we're assuming we already know what the electric field is. It's just a point charge. We've done this already. But Gauss's law will eventually help us find the electric field for distributions that we don't know. But we have to remember that this surface, two things about it. Number one, it's a closed surface. There must be an inside and an outside. Imagine that this charge is in the center of this balloon. There's a clear inside, and then there's a clear outside, like all out here. That's the first thing. The second thing is it's not real. It's a mathematical fictitious surface that is placed at my point of interest. I want to know what is the electric field there. I place my Gaussian surface there. I wrap it in a balloon of that R. Okay, let's look at a second part of Gauss's law. So Gauss's law first starts to relate the flux to that electric field. We did that. The second part of Gauss's law says, wait, let's relate that flux to the charge that is inside that surface, to this little dude right here. We kind of already did that, right? We said, wait a second, I got this. The flux was 4 pi KEQ, right? We just found that. Like we literally just did that. So I can Now relate the flux to the charge inside my Gaussian surface. Let's do one more thing. Let's do one more thing. So from that equation, let's remember that Ke and epsilon naught are related. So we had this. We had 4 pi Ke times Q. Wait, 4 pi Ke, that's 1 over epsilon naught. This is Q over epsilon naught. Bow. The flux is also Q over epsilon naught. But what Q? Not any random Q. All the Q enclosed. Enclosed where? Well, enclosed within this Gaussian surface. Everything inside that Gaussian surface. I don't care if there's a charge over here, because the electric field is only going to be affected by the net flux that comes from inside to outside. It's one of the beauties of Gauss's law. If I want to know what the charge is at point E, at point P, I put a balloon around it and I look at how much charge is inside of it. If I know how much charge is inside of it, I know epsilon naught is just a number, I can find the flux. Wait, and also, didn't we also say that the flux was E dot dA? We sure did. So this tells me that I can find the electric field given the charge enclosed in a Gaussian surface. Okay, we're not at final form yet. We're still looking at pieces. So the second piece that we're looking at is this. I can find the flux two ways. I can find the flux by doing that whole E dot dA. This is pure mathematics. But Gauss now starts to apply it to a little bit of physics and says, wait, that flux is also represented by the charge inside that surface, enclosed within that surface. And guess what? The net flux is totally independent of the surface that you enclose it in. What is the net flux? Do I know the charge? Yep. Do I know epsilon naught? Yep. Therefore, I know the flux. So it doesn't really matter what shape, what surface you enclose it in, right? I can have these like wobbly balloon-like things as long as it's a closed surface. And if I can figure out how much charge is in there, now I know the flux. And the flux is the same through all of these surfaces. It doesn't matter which one. I can imagine that it's probably easiest to use a surface like that, but it doesn't matter. It doesn't matter. Okay, but be careful. It has to be a closed surface. And guess what? If there's no charge inside this closed surface, then there's no charge. Then that equals 0. And the flux equals 0. So if I want to know something about this charge, I want a surface that encloses that charge. I don't want a surface that encloses a non-charge. It's 0. Surface isn't surrounding Q. Q inside the surface is 0. So back to this problem. Is there a charge inside this cube? Nope. How much charge is enclosed within this cube? Big fat 0. So that means that the flux is equal to 0. Yeah, we did that already, looking at all our E dot dAs. But we can also, like, legitimately just look at this, say, is there a charge in there? No, no flux. Now we're still not at the final form. We're looking at all the bits and pieces. Bam! There's my final form. Here's Gauss's law. So you have to remember, through all of this, you have to remember that Gauss is a mathematician. It's a big thing to remember, right? Okay, so check it out. First, Gauss says, hey, mathematically, two vectors, dot products, surface, that tells me basically like the density of the electric flux. Then he applies some physics to it and says, wait, if we're talking about electric flux, that's also related to the charge enclosed within that fictitious Gaussian surface. Usually, the way physicists use Gauss's law is to look at these two things, right? Because usually the things we're speaking of are electric fields and charges. So we're going to focus on setting those two things equal to each other. As you're doing the homework, there is some homework that asks you about electric flux. So either if you see a charge, you go directly there, or if you've got things about electric fields and dAs, you go there. But for the most part, we use Gauss's law to find the electric field, and we use that by looking at charges. So Gauss's law, super important, have it written down in its final form with all three things equal to each other. And always remember, do the vector first, then the calculus. First the vector, then the calculus. Cool, so let's do some examples. Okay, now, whenever you look at Gauss's law, the first thing to note is that you're going to put your Gaussian surface at the place where you're interested. If I want to know what the electric field is over here at some point, I'm going to place my Gaussian sphere right there. And I'm going to look at all of the charge inside of that Gaussian sphere to find it. Now, could I use another tool to find the electric field there? I could. What could I use? Well, it's what we did last time. I could do the integral of dq over r squared, right? And then be careful about like, well, the r, right? How does that change throughout the distribution? And does my angle change? Oh, yeah. That seems a little bit complicated, right? It was really good for like a straight line. It was really good for like a curved wire. But for a sphere, here's another way that might be easier. I want to know what the electric field is there. I'm going to put a balloon around it. For part B, it gets a little bit more interesting because now I want to know what is the electric field inside this thing. So imagine that this is a solid sphere. So it's solid. It's like a bowling ball. It's not a shell. So there's like charge all throughout here. Now I want to know, what does the electric field like inside this thing? Almost think of this as like planet Earth. And I could find what is the electric field at the surface. I could find what is the electric field at, maybe where satellites are. But I could also say, hey, I'm a geologist and I want to know what the electric field is inside planet Earth, like maybe where one of our mantles is. Okay? So where do you want to know the electric field? That's where you place your Gaussian sphere. Why am I using a sphere? Well, if my charge is a sphere, my surface is a sphere. If my charge is a cylinder, my surface is a cylinder. Why? You want to mimic the dA matching your surface to your actual object. the electric field goes radially outward. So look how easy that is. All my electric fields line up with all my dAs. Okay, let's look at this cylinder. We're going to look at cylinders later. Let's say the electric field goes out this way and out this way. Well, then if I choose a cylinder, then also my dA, whoops, wrong color. Then my dA also points that way. Come on. And then I've got thetas of zeros. What if I choose a different surface? Well, the thing is, like, Gauss is like, dude, you do you. You do you. It'll totally work. Mathematically, it'll work. Gonna make your life difficult, but it's gonna work. What am I trying to say? Oh, I'm trying to say all kinds of stuff, folks. All right. Here's my charge. And it's got a distribution, right? It's like a bowling ball. It's not like a little tiny charge. It's like a big, big old bowling ball. And I go, all right, I want to know what is the electric field here. But Gauss told me, he said I could use any surface I want to enclose. I'm going to enclose it in a cube. Cool. Do that. You do you. And like Gauss's law will work. But here's the problem. It's going to be hard. Let's look at all the dAs. Perpendicular. Right? All the way through the normal. This way, this way, this way, this way, this way, this way. Those are all the dAs, right? All right, what about the electric field? Well, the electric field from a positive charge points radially outward. So cool, up here you line up, but now you don't. And, well, that wasn't drawn very well. And here you line up, and here you line up, but you don't there, and you don't there, and you don't there, and you don't there. So now I've got to find all these angles that are constantly changing, right? All of those E dot dAs are going to have all like changing angles as you go around, continuously changing. What a hot mess. Gauss is like, it'll work, yo. The math is legit. But like, why make your life so difficult? Instead, why don't we match the distribution? Here's my charge. I want to know what the electric field is there. Let's use Gaussian surface distribution. I usually draw it as a dotted line. Don't know if it's gonna, nope, that didn't work. I usually draw it as a dotted line just to kind of remind myself it's not a real thing. And it's not a circle, it's a sphere. It's a whole balloon. And I was supposed to do that in green, but that's okay. So here, dA, here, dA, here, dA, here, dA. Let's do one right in the middle, somewhere over here, dA, somewhere over here, somewhere over here, right? And now, how does the electric field point from a charge? I'm going to use blue just to see it a little bit different. Well, the electric field points radially outward. Lines up here, lines up here, lines up here, lines up here, and basically lines up everywhere I go. They are both radially outward. So I can be super smart in how I approach Gauss's law. And if I match the distribution everywhere along the way, theta is equal to 0, and cosine of 0 will always and forever be 1. So if your charge is a sphere, make your Gaussian surface a sphere, because your other option while it works is a hot mess. Okay? All right. Where were we? Let's see. Oh yeah, we were doing this example. So that was the long way of saying, wait, why am I choosing a spherical balloon to wrap it in? Right? That's why. Do you have to? No. Should you? Yeah. Cool. All right. So remember how I said we were going to do volume integrals? Oh, now's the time. Remember that volume charge density? Yeah. That means that every little cubic meter has some charge in it. This was charge per meters cubed. It's a bowling ball, right? It's solid. So the total charge is Q. Rho is the total charge over the total volume. That's from our previous topic. One more thing is that it's uniform. What does that mean? It means it's non-changing. It means it's not changing. So yeah, the totals, but also a bit of charge is a bit of the volume, and a little amount of charge is a little amount of the volume. We'll look at that in just a second. Because it doesn't change, I can look at it in terms of totals, I can look at it in terms of differentials, or I can look at it in terms of what's inside. Okay, every little cubic meter has the same amount of coulombs. So I can look at the total cubic meters, or I can look at a little itty bitty part of the cubic meters. Our density will not always be uniform, but for now it is. Okay, so an insulating solid sphere. What does insulating mean? It means the charge stays where we put it. It's like plastic and it stays where we put it. It's not free to move around. We can make it move around, but we're leaving it alone. It's going to stay right where we put it, which means that it's pretty much evenly distributed all throughout, which is what this means. Uniform. So that means that I can look at a little itty bitty bit and it'll have rho. I could look at a huge bit and it'll have rho. I could look at the entire bit and it'll have rho. Rho doesn't change. Why? Because it's uniform, whether I look at a little piece or the total. Now it carries a total charge Q, and we know it's positive. All right, so first, we want to find the magnitude. We already know which way the direction goes. The magnitude of the electric field at a point outside the sphere, right? So our sphere has a radius of A. We want to be at R greater than A, outside of the sphere. So that's this over here. That's the easy one. And in fact, we already know the answer. Okay, but let's do it. And then we're going to come back and do the harder one. All right. So for R greater than A. Okay. So let me draw my sphere. Here's my sphere. And it has a radius A and it has positive charge Q. I want to know what is the electric field at some distance R greater than A. So up here somewhere. Okay. And that is R. I want to know what is the electric field at R, at that point. So I'm going to place my Gaussian at that point. That's where I place my Gaussian. It's fictitious. Okay, so Gauss's law says the electric flux can be defined two ways. Look, first of all, we can look at E dot dA. And second of all, that is also related to the charge inside, enclosed over epsilon naught. Inside what? Enclosed within what? Enclosed within my Gaussian. And I'm going to equate these two. What is Q enclosed? It is the charge inside the Gaussian surface. What is it? How much charge is inside my Gaussian surface? Well, it's capital Q, right? My surface is this blue part. My surface is this blue part right here. My blue part. How much is inside? Well, all of this Q is inside of it. So that's where this comes from. Oh, all right. So we're going to relate those two things. So let's start and let's say we have two pieces of the puzzle. E dotted into dA is equal to the charge, sometimes I write it as inside my Gaussian, over epsilon naught. Okay, so let's look at each of these. First of all, do the vector. This is magnitude E, no longer a vector. Magnitude dA, no longer a vector, times the cosine of the angle between them is equal to, what is the charge inside of my sphere? Total Q over epsilon naught. Okay, what was theta? Theta was 0, right? Remember that everything pointed in the right direction. So that just meant that this is now E dA times 1 is equal to Q over epsilon naught. Okay, does the E field change anywhere on that surface? So let me do it. Oh wait, I have the drawing. Hold on, I have the drawing. I have the drawing. Little Thundercats throwback. I have the power. Anyway, so here, let's do this. E field is radially outward. Let's do E field in green. Radially outward at every point. I know we're doing this ad nauseum, but trust me, having a good Gauss's law foundation will take you a long way. Okay, so there's all my E fields, and then let's do all our dAs in blue. Let's keep those in blue. So this little surface element right here points in the same direction, same direction, same direction, same direction, same direction, same direction. Theta equals 0 all the way through. So that's the advantage, right, of doing that distribution. And then the charge enclosed, how much charge is inside of this blue surface? How much? Well, all of that capital Q. All right. Oh, I know what I was going to ask. Back here. Does the magnitude of the E field change on this surface? In other words, is the E field different for, say, is the E field here different than the E field there? different than the E field there, different than the E field there? No. They're all equidistant, right? And E field, like, it's going to be the same as long as you're at the same distance from it. So the E field doesn't change. So it can come out of the integral. Okay, so I've done my vector, check. Now I can do my calculus. So E comes out of the integral. And then I'm just going to integrate the surface, little bits of the surface over the whole surface. And what I'm going to get is, well, I just get the area back is equal to the total charge over epsilon naught. What area? Gaussian area. What was my Gaussian? My Gaussian area is for your fictitious Gaussian, which in this case was a sphere of radius r. So my Gaussian surface is 4 pi r squared equals q over epsilon naught. Hey, E is equal to q over 4 pi epsilon naught r squared, which we could write as KEQ over r squared. Well, it seems like we already knew that. But there's our answer. So, all right, hold on. Here we go. So here's our answer, right? And it kind of seems like overkill to do that. But let's look at part B. There really is no way of doing part B other than using a Gaussian surface. So now we want to know, what is the magnitude of the electric field at a point inside the sphere, inside of it. Okay, so what we have to do is then we've got to place our Gaussian surface inside. We want to know what the E field is inside. Well, then our Gaussian balloon has to be inside. And we want to know how much charge is inside of that. It's not the total charge. There's some charge out here that is outside of our Gaussian. So we've got to somehow figure out what that charge inside is. Has the shape of our Gaussian sphere changed? No, it's still a Gaussian sphere. So you know what? That A is still going to be 4 pi r squared. That holds here. That holds here. Just the value of r has changed. My charge is still a sphere, so my Gaussian is still going to be a sphere, and a sphere is always going to have a surface area 4 pi r squared. It just doesn't change. What does change now is this. So over here, Q enclosed, well, all of it was inside my Gaussian. Right, here's my Gaussian, all of it was inside. Here, Q enclosed, we have to really think about, and it is not going to be the total because there's some stuff out here that I'm not going to consider. I only want to know whatever is actually inside. What is inside? The green part. What is that? It's not the total. So let's set that up. And it's kind of hard at first. Well, like physics is always like that. There's a saying that says physics is impossible until it becomes obvious. I'm still waiting for it to become obvious. It's still kind of impossible. But like physics is hard. And then Gaussian, it can be really complex, but once you get the hang of it, it's a pretty cool tool. Okay, so now let's do for when our Gaussian is inside our sphere. So now, I'm not going to redraw, I feel like I've already done that. Our charge inside our Gaussian is not the total charge. I am going to do this. Here's my total charge Q. And Q total is going to be in, what color is that? That's right. My Gaussian is inside of here. So my charge inside can only be the blue. I do not need all of this charge out here. I don't need that. I only need the charge inside my Gaussian. And that's where we have to focus on. Okay, so this is where we really look at our charge distribution. So this had uniform volume distribution. The uniform means that I can write it as Q total over V total, means that I can write it as Q enclosed with my Gaussian over the V enclosed of my Gaussian, means I can write it as my little bit of Q over my little bit of volume. The uniformity allows me to say, hey, because it doesn't change, I can look at the whole thing, a little bit of thing, a differential of thing. It doesn't matter. It's uniform. So I want to know what this Q enclosed is, right? This Q enclosed. I want to know what that is. That's this bit. That's that little blue bit right in there. So that means that I have to relate it to the volume, not the whole volume. What is the whole volume? Well, the whole volume, let's see. This is A. The whole volume, what's the volume of a sphere? Is 4/3 pi a cubed. Okay, so what is the enclosed volume? Well, it's still a sphere. It's still a sphere. It's just a smaller one of radius r. So 4/3 pi r cubed. So how can I write my charge enclosed? Well, then my charge enclosed within that, well, that's going to be rho. That's just a number. It's just a number. Times the volume enclosed, my Gaussian. Hold on to that. Let's write out that Gauss's law. So we're going to relate our enclosed charge over epsilon naught to what? To the integral of E dot dA. Okay, and do we agree that E and dA point in the same direction so that cos equals 1? Do we agree? Let's look back at our drawing. Sure, I've matched the distribution. My distribution, the red, is a sphere, and the Gaussian, the blue, is a sphere, right? So my electric field lines point radially inward and outward. My dA points radially inward and outward. Yeah, let's do it. Let's just do a couple. So let's see. dA would point out this way, and well, the electric field, right, would go along this axis as well. And dA and electric field. Right? All the way around, everything is radially outward. So I would agree that in effect, everything points in the same direction. Check. Cosine theta is equal to 1. So I do my vector first. So I have charge enclosed in my Gaussian over epsilon naught is equal to integral E dA. I took care of the vector, dot product gone, and now I've just got magnitudes. Okay. Is the electric field going to be constant? Yes, I'm equidistant still. That hasn't changed. I'll let you know when it changes. So it's going to come out of the integral, and I'm going to integrate the whole area, little bits of area until I've got the whole area done. So this is just going to be EA. All right, so the charge enclosed over epsilon naught is equal to EA. Now this is the area of my Gaussian. I know what that is. The area of my Gaussian, remember, was 4 pi r squared. I know what that is. Where's my Gaussian? My Gaussian is this blue. Here's my Gaussian, it's the blue. My Gaussian has a radius of r. The area, okay, so a Gaussian is 4 pi r squared. See, my Gaussian is with r. All my totals are with a. So the Gaussian is 4 pi r squared. Cool. Now what? Well, now I want to focus on this. Right? What do I do with that? I still have to figure that out. So let's do that on a new whiteboard. Let's look at that. Q enclosed within that Gaussian. Well, remember we said we can write that as rho times the volume enclosed by that Gaussian. Rho is just a number, we'll keep that. What was the volume enclosed? My Gaussian, right? My Gaussian goes with A. Nope, my Gaussian goes with R. So the volume is 4/3 pi r cubed. Cool. But I want my answer in terms of Q's and R's and A's. Not rows. Not row. So I want to get rid of that. Okay. Well, remember, rho, I can speak of it as total over total. I can also speak of it, because it doesn't change, as enclosed over enclosed. Right? I used this one here. But I want my answer in terms of capital Q. Well, here's my capital Q. Here's my capital Q. So I'm going to rewrite rho as Q over V total. What is V total? Wait, the totals go with A. 4/3 pi A cubed. The total volume of that sphere, not the enclosed volume. Not the enclosed volume. So Q enclosed, instead of rho, I'm going to write Q over 4/3 pi A cubed. And V enclosed is 4/3 pi r cubed. So 4/3 cancels 4/3, pi cancels pi, and my charge enclosed is the total charge times a ratio of r cubed over a cubed. These little tricks we're going to do a lot. It is really important to remember that as long as our distribution is uniform, you may speak of the totals or you may speak of the enclosed. Okay, so if we want to put it all together, right, because we were here, So now we want to put it all together because now we know how to rewrite Q enclosed. So let me get a new board and just rewrite this. So where were we? We had gotten to the charge enclosed over epsilon naught is equal to EA. A of what? A of my Gaussian. A of the Gaussian. Now let's replace a couple things. Let's replace charge enclosed. What did we say it was? We said it was the total Q over R times R cubed over A cubed. Okay. And then the area of our Gaussian area of a sphere is 4 pi r squared. So put that all together. We have q r cubed over a cubed epsilon naught is equal to e times 4 pi r squared. And this r squared will cancel with two of them over here. And I'll solve for the E field. The magnitude of the E field is QR over 4 pi epsilon naught A cubed. Which, if you remember, can also be written as KEQ R over A cubed. All the same. Doesn't really matter. Now, what if I wanted to write it in terms of rho? Right? Not in terms of Q, but like in terms of rho. Well, then I would just leave the rho here with Q enclosed. What would that look like, you ask? Let's see. Let me get... So let's say we know rho. We just know what it is. It was given to us, right? So we had this 4/3 pi r cubed. And let's say we know rho. So then we've got Q enclosed over epsilon naught is equal to EA of my Gaussian. Then I would write it as rho times 4/3 pi r cubed over epsilon naught is equal to E times 4 pi r squared. And then 4 cancels 4, pi cancels pi, the squared cancels one of those, and I get an E field that is equal to rho r over 3 epsilon naught. They're all the same. Let's put them all on one whiteboard. Why do I keep doing the wrong button? Let's put them all on a new whiteboard. I have 3 ways to write this answer. They are all perfectly equivalent. I can say KEQ R over A cubed. I can say, where was the other one? I can say Q R over 4 pi epsilon naught A cubed. And I can also say that it is 3 equal to rho r over 3 epsilon naught. These are all exactly the same, and tell me what is the E field inside that sphere. I would use either of these two if Q is known. And I would use that if rho is known. They're all the same. Okay, so what we do when we look at Gauss's law is this. We're going to focus on E dot dA is equal to charge enclosed over epsilon naught. And your brain power should go right here. That's the one you want to figure out. What is Q enclosed? How much charge is inside the Gaussian surface? How much? And then you also need to remember that this A is of your Gaussian. So your charge enclosed, okay, can be couple things. It can be a combination of rho times V enclosed. Okay, it can be a lot of things. So actually, before you do that, we really have to then, you really have to go back to those definitions and say, okay, so if I'm talking about rho, that's charge over volume. But if it's uniform, I can look at the totals or I can look at bits and pieces. We could also have a surface. And if it's uniform, we can have the total over the total surface or a little bit of it over the little bit of surface. This holds for uniform rho or sigma. And that's the stuff that you want to work with. So your brain power is going to come here to charge enclosed. If you've chosen a Gaussian that is a convenient Gaussian, that dot product will usually go away, right? If my distribution is a sphere and I've chosen a sphere, then all those dot products are one, right? So if my distribution is a sphere, my distribution is a sphere, my Gaussian is a sphere, everything lines up, and all of those thetas will be 0. So if you choose a Gaussian wisely, your left-hand side usually just becomes EDA. You take care of the vector by choosing a Gaussian wisely. How do I choose a Gaussian wisely? Just match the distribution. If my distribution is a cylinder, guess what I'm going to do with my Gaussian? Yep, a cylinder. Can I choose something else? Absolutely. I could choose a Gaussian that's a sphere, but then I've got a whole hot mess of my dA pointing in all random directions and not quite lining up with my electric field. Sometimes yes, sometimes no. So I don't want to do that. So if you choose your Gaussian carefully, that E dot dA just becomes EDA. So we'll come back and we'll do some more examples, okay, of different distributions. So we've done a sphere. What is the electric field outside? What is the electric field inside? Next, we're going to do like a cylinder, like a line of charge. And if I enclose it in a cylinder, I see that all my vectors line up. If I choose a different distribution, not quite going to work. Then we're going to look at what happens when it's not uniform. Where does that come in? No, that's still uniform. We're going to get to non-uniform. There we go. We're going to get into non-uniform distribution. That's going to be fun. And then we're going to talk about conductors and look at conductors and insulators together. Woo! All right. So, I'm debating whether I should do this now or later. Well, you know what? Y'all can pause the video. Pause the video. If this is like you're like done, I know it's super hard to watch, like just like watch a video, right? So again, I expect that you work on a couple problems, you take a break, come back to it. So now's probably a good time to go pause, take a break. But I'm gonna do one more example. All right. So now I have a line of positive charge. Okay, so a line of positive charge that's infinite. That means it just goes all the way. And if it's positive, then that means that the electric field, like over here, I've got like a top-down view. That means the electric field goes radially outward, which is why I want to enclose it in a cylinder. Think of the wire as a cylinder, right? So I'm going to enclose it in a cylinder. So wires get enclosed with cylinders. Spheres get enclosed with spheres. And now this now has charge per unit length. So we're looking at lambda, not rho. Okay, so let's draw this. We choose our Gaussian carefully. We have all our E's and dA's lining up, right? You can see it better over here. All your E's are radially outward, but also all your dA's are radially outward. So they all line up perfectly. Okay, so all the way around, your theta is equal to 0. All right, let's get a whiteboard. Okay. Oh. So this is called cylindrical symmetry. Okay, so cylindrical symmetry means that we're going to not do that. We are going to draw our line of charge. Come on, pencil. Draw our line of charge here. And remember that it's positive. And it goes to infinity, so I don't really know where it ends, either top or bottom. So I don't really care about the top or bottom. All I care about is the electric field lines are going to point out this way, both sides. I mean, if I could eventually find the end, it would point out this way, but it's infinite, so I can't find the end. So I'm just going to look at my electric field lines going out this way. Well, that means I want a Gaussian that has dA's that point in that same direction so that those angles go away. That's why we choose our Gaussian carefully. So remember that dA is normal to the surface, so that means I want a surface that is up and down like this, and I can imagine the same thing happening over here. So yeah, I'm looking at a cylinder, so all those dA's line up. Okay. My Gaussian is going to have a length L. I need to know that. So I'm going to need to know something about areas and stuff. Okay. So now my Gaussian is equal to a cylinder, and the cylinder has a radius of r. Okay, so this is R, and it has a height of L. My charge has a positive, and I know it has lambda, which is uniform, and that's all I know. Just positive line charge. Oh, and it's infinitely long. So I don't care about the top and the bottom ends. Okay, so let's set up our Gaussian. Well, no, we already set up our Gaussian. Let's set up Gauss's law. Gauss's law says E dot dA is equal to the charge enclosed over epsilon naught. Oh, I think I don't know that I said this. Why am I choosing my Gaussian outside of my wire? Because I want to know what is my electric field where at some point R. I place the Gaussian at R, at the point of interest. It's really hard to write today. It's also really hot. Okay, point of interest. That's where I place it. So I clearly want to know what is the electric field at that point, at anywhere, at some R. Okay. So back to here. Okay, so so if I look at, I mean, we're pretty clear that E, dA point in the same direction, theta is equal to 0, cos of 0 equals 1. So that E dot dA, do the vector first, becomes E dA cos theta becomes just E, come on, just E dA. Electric field is not changing. I'll let you know when it does. E dA is equal to EA. Is it always true that integral E dot dA defaults to EA? No. Many times, yes. Always, no. We'll see when that's not the case. When the E, this shortcut will always hold for E constant, and we'll see when E is not constant. Okay? I will let you know. Okay, so left-hand side, we chose wisely, therefore we can just use EA. Check. That's not what I wanted to do. Check. Where do you set your brain power? Right here, Q enclosed. How much charge is enclosed within that? Okay, what is the charge enclosed? I don't know, but I know that I have this charge distribution. And what is this charge distribution? Well, it's uniform. So this tells me that it is equal to the total charge over the total length. It is, because it's uniform, it is also equal to the enclosed charge over the enclosed length. The Gaussian length. What's my enclosed length? This, blue, this is my enclosed length. It's the length of my Gaussian. So I can write my charge enclosed, right? I can write my charge enclosed then as my charge distribution times my Gaussian. Okay, put it all together. So we had on the left-hand side EA, and on the right-hand side we had that. Okay, so take the steps. Area of my Gaussian is equal to what? Charge enclosed. Well, we're going to write that as lambda times L enclosed, which is just L, over epsilon naught. What's the area of my Gaussian? The area of a cylinder is what? Well, it's 2 pi r times the height. Is my Gaussian at r? Yeah. Remember, I place my Gaussian at r. So E times 2 pi RL is equal to lambda L over epsilon naught. And guess what? It doesn't matter how long you make your cylinder. The only thing that matters is placing it at your point of interest, R. Therefore, we have an E field at point R, that is equal to lambda over 2 pi epsilon naught R. Boom, pow, bang. Hey, let's write it in terms of KE because we can. So remember that KE is 1 over 4 pi epsilon naught, but I've only got 2 pi epsilon naught, so then I've got to make this 2 lambda over, 2 lambda KE over R. Same. Doesn't matter. And that will always hold for any type of a positive long distribution. Share 2 lambda KE over R. So step 1, choose a Gaussian surface that mimics the distribution. Choose a Gaussian surface that mimics the distribution so that all your E's and all your DA's line up. Step 2, place your R at whatever, wherever you're interested in. In this case, it was greater than the length of the wire, or than the radius of the wire. The radius of the wire was capital R. Lowercase r is for our Gaussian. And step 3, focus on charge enclosed. Okay. All right. That's enough for this video. Next video, we're going to look more at these charges and these sigmas, and more importantly, start talking about what happens when it's non-uniform. So start practicing homeworks, but only like sphere distributions and like long cylinders. You're not prepared to do the rest yet. So we'll continue next video. Bye.